All right, so we're going to pick this back up. The key to predicting precipitation reaction is understanding that only insoluble compounds form precipitate, so you have to look at the solubility rules. In a precipitation reaction, two solutions containing soluble compounds combine to form an insoluble compound, which is a precipitate. All right, so we have here potassium iodide and lead 2 nitrate, and they combine to form lead 2 iodide and potassium nitrate. If you were to look at the solubility rules, you would find that lead 2 iodide is in fact insoluble, so that is why we have solid here, so this is a precipitate. So what happens is you start with the potassium iodide, and you have an aqueous solution of that, and an aqueous solution of lead 2 iodide, and so you're going to mix those guys together, and when you mix them together, right away, before anything happens, you're going to have all of these little ions together, and then they're going to swarm and figure out who they are going to mix with. So remember, it is the cation of this one that's going to mix with the anion of this one, and then the cation of this one that mixes with the anion of this one. Okay, so that's how we get our products here. And after a moment, they go ahead and mix together and form your insoluble ionic compound. That is your lead 2 iodide, and so that would be like a little solid here floating in your solution. And then what's left over are your potassium ions and your nitrate ions. All right, so we're going to try this one here. So this one says, write an equation for a precipitation reaction that occurs, if any, when solutions of sodium carbonate and copper 2 chloride are mixed. All right, so I need to write this out. I need to look at the charges first. I know that sodium is in row 1, so that is a +1 charge, and carbonate is CO3 2-, that is a polyatomic ion. All right, so these guys would go together. We need to make sure, just like from chapter 5, that the charges are balanced, equal but opposite. So I would need 2 sodiums to balance with that carbonate. All right, so I would start out with Na2CO3. All right, and it says we're mixing with copper 2 chloride. All right, copper, this 2 here implies that it's Cu2+, and we know that chloride is Cl- because it's in the -1 row. All right, I would need 2 chlorines to go with that 1 copper, so this one would be CuCl2. All right, these guys are both aqueous if you were to look at the solubility rules. All right, and we need to see what they form. So keep in mind that the cation of this one is going to go with the anion of this one and vice versa here. But I do need to look at the charges. So sodium I know is a +1 charge, and I know chlorine is a -1 charge. Okay, so those guys just go together. They're already equal but opposite. So it becomes NaCl. Okay, and then we have our copper 2+ that's going to go with our carbonate, and carbonate is a 2- charge, so those are already equal but opposite. So it's going to become CuCO3. Okay, so now we're going to take a look at those solubility rules. All right, when you have a sodium ion, you are going to be soluble. Okay, so we know that the first one, NaCl, is soluble. So I'm going to put an AQ right here. And then let's look at the copper 2 carbonate. And you'll see that with the carbonate that you are insoluble. Okay, so let's go back. And we're going to write that this is insoluble, which is a solid. All right, so let's now see what they did. They started with the formula like we just did, okay? Then the cation of this one goes with the anion of this one and vice versa. Okay. Then it tells you to take a look at the solubility rules, which we just did. We went back to the page and looked at the solubility rules. We found that NaCl is soluble and CuCO3 is insoluble. Now, if all of the products were soluble, then that would mean that there was no precipitate, and you would write no reaction next to the reaction arrow. So it'd be like, you know, da-da-da-da-da plus da-da-da-da-da goes to NR, or you could write out no reaction. But that is not the case in this particular situation. Okay. All right. Now, because this example has an insoluble product, we need to continue to the next step. Write it out, which we just did on the previous page. Then, whoops, I went a little too far. We need to make sure that it balances. All right, so when I look at this, first thing I see is that my sodiums, I have 2 sodiums here, and here I only have 1. So I'm just going to throw a 2 out in front and try that. Okay, now that gives me 2 chlorines, and I have 2 chlorines, so that looks good. To me, it looks like we have everything, but I like to go back through. So 2 sodiums, 1 carbonate, 1 carbonate, 1 copper, 1 copper, 2 chlorines, and 2 chlorines. This one's balanced. Very nice. This is just a reminder when you do your balancing to balance the coefficients and not the subscripts. Excellent. Next, we're going to talk about acid-base reactions. So in an acid-base reaction, you are, well, clearly going to have an acid. The acids, to me, are very easy to spot because you have the H out in front. Acids are always aqueous. And a base, you're just going to have to memorize the acids and the bases. I always suggest flashcards for that. And when you mix these, you're always going to have a water and a salt. A salt is just an ionic compound, okay? So you'll see here, a lot of times I like to write the water as, you know, well, I underline the H and the OH, and I know that that's the water, HOH. And then whatever's left over is your salt, so you have to put the cation first and then the anion. But I think just kind of seeing that water is an H and the OH, you can kind of pick those out of there. All right. So acid-base reactions, you might also hear them called acid-base neutralization reactions. They form a salt and a water, and yep, there you have it. Net ionic equation is H plus and OH go to H2O. All right, so here are some common acids and bases. I really would just suggest memorizing these. I just think it's the easiest way. Here is an example of an acid-base neutralization reaction. I have sulfuric acid and potassium hydroxide. Okay, I know that acid-base reactions always produce a water and a salt. Okay, so I'm just going to write that water first, H2O. Okay, and then I'm going to, I just like to kind of underline the OH and the H just so that I can see that they're out of there. And don't worry about the fact that they don't balance right now. We're going to balance them at the end. All right, what's left is your salt. Okay, so you have your potassium and your sulfate. All right, so I'm just going to write in these little areas a little bit. Potassium, I remember, is a +1 charge, and sulfate is SO4, 2- charge. Okay, so how many potassiums would I need to balance with this sulfate? I would need 2. Okay, so 2 potassiums for that 1 sulfate, and it becomes K2SO4. So we need to write our phases in here. The water is liquid. And this is one of the rules on the solubility rules with the potassium, that it is going to be aqueous. All right, so now we need to go through and make sure everything balances. Let's see, one sulfate. I see that I have 2 potassiums here, but I only have 1 here, so I'm going to throw a 2 out in front there. Okay, so that gives me the 2 potassiums, which is good. But I notice here, let's see, that I have 2 hydrogens plus 2 more hydrogens on the left, so I have a total of 4 hydrogens on the left, but on the right I only have 2 hydrogens. Okay, I cannot go in and change the subscripts, right? So I'm just going to throw a 2 out in front here, and if I throw a 2 out in front, that gives me 4 hydrogens on the right-hand side. Okay, gives me 2 oxygens, which should be good. So let's check this out. I have 2 plus 2 more hydrogens, a total of 4 on the left, and I have a total of 4 on the right. And for oxygens, now we're not going to pay attention to the oxygen that's within this sulfate here, because this sulfate is also a sulfate over here, so we're going to count those guys as 1 unit. So I got my 2 oxygens here, and I have 2 oxygens here, so that one's really good. All right, I have 2 potassiums here and 2 potassiums, so that balances. And I have 1 sulfate on the left and 1 sulfate on the right, so that one balances. Let's try another one. All right, so I picked phosphoric acid. This is not one of the ones that you have listed on the table above, but this is an acid. And I chose barium hydroxide. All right, so I know that when I have an acid and a base mixed together, I'm always going to have a water and a salt. So I just kind of like to underline the H's and the OH's so that I can see that those are being taken care of right here. So H2O, and I know that that's a liquid. All right, so what's left over is my barium and my phosphate. All right, so what charge does barium have on it? Barium is in the 2nd row on the periodic table, so that's your +2 row. Okay, so I'm going to write that off to the side. Ba2+, and phosphoric acid is, PO4, phosphate is PO4 3 minus. I had to think about that one. 3 minus. And so how would these guys go together? I would do the crossover rule here. I would need 3 bariums and 2 phosphates. So that would go like this. Ba3 PO4 2. I pulled up the solubility rules real quick here to show you that phosphate is insoluble. All right, so we're going to make this one balance. I notice that I have 2 phosphates over here, and here I only have 1, so I'm going to throw a 2 out in front there. I notice that I have 3 bariums over here, and here I only have 1, so I'm going to throw a 3 out in front there. Sometimes it might not always work out perfectly, and you got to erase. I've done it many times. So let's see where we're at. I have 6 hydrogens so far on the left, plus 6 more hydrogens. That's a total of 12 hydrogens. I only have 2 over here, so I'm going to add a 6. That gives me 12. I have 6 oxygens, okay, but here, look, I have 2 times 3, which is 6 oxygens. So this one balances. I have the 12 hydrogens, the 2 phosphates, 2 phosphates, 3 bariums, and 6 oxygens. So this one balances. Excellent job. That was a tough one. In our final video, we will be talking about oxidation and reduction reactions. Excellent job. See you next time.